am Dr. Rashmi Sharma from Department of Information Technology. Today we would be discussing one of the important topic of Unit 3 of Blockchain Architecture, which is in third year, 6th semester of BTech IT Information Technology. The topic is how the transaction flows in Hyperledger Fabric. So, topic covers would be Hyperledger Fabric V1 architecture, then transaction flow, steps involved in that particular transaction flow, and what do we mean by ordering services, and what are the different ordering services which we apply in Hyperledger. Then the main keywords are Hyperledger Fabric, nodes, ordering services, channels, and Fabric peers. So this is the Hyperledger Fabric architecture, that is called as the V1 architecture. Coming to the point, this is an overall architecture. We have three main entities involved into this. But when all these entities are interacting with each other, we should have some authentications which take into consideration. As we know that blockchain depends on security, that gives you a privacy. So we should have some certificates through which we can interact with each other, so that I know that you are the authenticate user who is sending me the information. And you should also know that I am the authenticate user, and you should encrypt that particular message which you are sending, or the block which you are sending, with my public key, so that I can decrypt it with my private key only. So there are some of the I think the unique IDs which are being given, like we have a unique ID as I'm working in a college, so I have a unique faculty ID, students have a unique student ID or the university roll numbers. Similarly, we have certification authorities which give these particular members which are there a unique number, so that we a combination of the public key and the private key, so that whenever they interact with other, they use this particular public key encryption. So here each and every this is an optional thing. Every Hyperledger Fabric has this Fabric CA, that is certification authority. When you are a member of this particular Hyperledger architecture, then you can have external CAs or the internal or the Fabric certification authorities who give a unique ID along with a combination of public and private key to each and every users. And these particular things are being kept or requested through admin. Whenever we join a new organization, then we go to the HR person, then they send us to the admin department where they give us our credentials. So these are credentials through which we are being uniquely known in that particular system. So this certification authority gives signing credentials, and when you use these particular credentials, the person who receives a message identify you as a person who is authenticated to send the message. Means these credentials combines your public key, your private key, and how many people you can get connected to, or who all are there in your group, and what are your rights. Okay, like you have a read, write, update, right, whatever functions you can perform or whatever rights you have all those things as a credential in this given to you by certification authority. Now comes the nodes. Obviously here the peers, these peers can be of three types. One is endorser, another is committer, and third one is the orderer. This is the first one, endorser, second the committer, and third one is the orderer. So and every peer which is there in this particular architecture can act as an endorser or a committer or an orderer. The same node can be an endorser also and a committer also, but the all those particular chain codes which are there, those are here. Your chain codes are here. See, you don't have any chain codes or your business logic in this ordering services. How do you access these particular endorsers? Definitely it is through your SDK, and here SDK is software development kit. Definitely here HFC is Hyperledger Fabric component. component or client, whatever you can tell. If it is an application, that would be a client. So obviously a client application interacts through SDK, which is built on your Hyperledger fabric, and then it sends the request to your endorsers or committers anywhere. So first you endorse those particular transaction. When you endorse this particular transaction, then it goes, these transaction needs to be ordered, and when these transactions are ordered, then you commit those particular transaction. While committing this particular transaction, definitely you have to perform some particular events on it. What are events needs to be performed depends on the chain codes or the logic which is developed in this particular chain codes. And when these particular things are being done, that is, the chain code is being executed, the events are being fired, and when you are done with all these particular operation, the date, your permanent changes are being stored in your ledger. And definitely these ledgers are distributed ledger, which we require in our blockchain architecture. So as Hyperledger is a blockchain, so these particular ledgers are distributed. Definitely these blockchains are also on different peers. How this particular architecture is being, this is a consolidated architecture. So detailed architecture we would be looking into coming series. So the three nodes which I told, one is the committing peers, which maintains the ledger and the state. See, they have to maintain the ledger. Definitely they commit the transaction. I think everybody knows how you commit the transactions in database. Similarly, we commit the transaction, we freeze those particular changes, and is be done permanently in the databases. Then may hold smart contracts of the chain king. That is the business logic. They may hold. That is not, if that particular node is a committer also and endorser also, then definitely that node will hold the chain code. If only the node is a committer, then it is an optional property. Then endorsing peers are specialized committing that receives a transaction. They propose, they have a proposal for the endorsement. There are some endorsement policies. We will look into the coming slides. What are the different endorsement policies we can have? One of example is, if I have 5 nodes, endorsement nodes, and if I design a policy that minimum 4 nodes should agree on this or reply on this particular transaction, then I would commit that, or then I will send this particular transaction for ordering. So minimum 4. If they do all the 5, well and good, but minimum 4 required. If I get a reply for only 3s, then I won't go that particular transaction for ordering and then committing, unless and until I get the minimum 4 replies. So there are some endorsement policies. So what all policies are feasible for that particular business domain is being seen by this. Then you response granting or denying the endorsements. If that particular person or the peer is capable of becoming an endorsement, or it can only commit, or it can only act as an order, is being decided by your admin. Then they would definitely hold the smart contract. So here the smart contract is compulsory because we are executing that particular business logic. Here is it is optional. Okay, this is optional, this is compulsory. Okay, now comes the ordering node. See, the color of each and every node is in sync with what we have done here. The blues were endorser, the creams, the gray were committers, and the greens were orderers. So here also the gray are the committers, the blue are the endorsers, and the green are the orderers. The orderers approves the inclusion of transaction blocks into the ledger, and then they communicate with committing and endorsing peers. They have to communicate. See, here we have communicated with the committers. So the same person acting as an endorser and a committer, then they would surely propagate that particular transaction to the orderers. So from orderers to the committers. It does not hold the smart contract. See, no option for smart contract, no option for your ledger. They don't have that particular ledger. So the detailed, so the basic flow which we have done is, first we endorse that particular transaction. So for endorsing, we have some endorsement policies which we have to take into consideration. When we are ordering it, I have some ordering policies also for executing those particular transactions. And when I have those endorsement policies fulfilled, then the ordering policies are being done, then we go for the validation of the transactions, and then adding that to distributed ledger is being done after the validation takes place. So this is the flow. Whenever we are having a particular transaction which is being done in a normal, first of all we validate that particular transaction. Like if I'm entering a particular node, if I'm entering a particular transaction, see, assume I have to withdraw a amount of 1,000 rupees. So first thing what the account would see, that if I have a balance of 1,000 rupees or not. If I have, yes, then I would be able to withdraw. If that ATM has a sufficient balance or not, yes, then I can withdraw. So here in normal transaction, what we do, we first validate, okay, and then we come across your card and your PIN number is being validated. Then you order those particular transaction, and then the endorsement is taken place. But in blockchain, the order is reversed. We validated the list first, we endorse, we have some specific policies for finalizing those particular transaction, then the ordering, and then the validation takes place. So all this I have 7 steps in which the transaction flow takes in Hyperledger. So one by one, each and every step is being described in the coming slides. So see, your application, your SDK, client application, the look and feel which client is having, the client is being transacting with different peers or communicating with different peers through your SDK. So client application, that is a GUI which you have, and then you communicate with your endorser. These dark blue ones, remember please, these dark blue ones, E0, E1 and E2 are your endorsement peers. See, I have written here endorsement peers. Then the gray ones, P3 and P4, are your committing peers. These 4 O's are your ordering peers. I think this is clear. Then you have these particular three boxes. This tells you have a distributed ledger which is there on each and every node. Either it is a endorser node, it can have this particular, it has to have this distributed ledger. Even your committing node should have that, because they would commit your transaction and then they would add into this particular blockchain. So they also have this distributed ledger. But your ordering services don't have these particular ledger. So ledgers are being associated with your endorsers and your committers. These orangish or yellowish boxes which have different names on it, AB, and here I have AD, these are my chain codes or my smart contracts which are being written or which are being to be implemented, or the business logic is to be implemented on these endorsers and the committer nodes. So all these particular chain codes or the smart contracts, here I don't have any smart contracts. So these are few smart contracts which is being written here. And this pink one shows me the endorsement policies. Okay. See, I have given one example of this endorsement policy in this slide. So here I have 2 policies. First one is E0, E1, E2 must sign the transaction. Means whenever this particular transaction is being committed, I require a response from each and every endorsed peer. So because E0, E1, E2, I have 3 endorsement peer, all these particular nodes should reply or sign that particular document. Okay, signing is, if I think we are validating that this is a valid user. Then the second is P3, P4 are not part of the policy. These are committers, so they are not a part of our policies. The client application submits a transaction proposal for smart contract A, and it must target the peers E0, E1 and E2. So when these particular requests, see, if R1 request is being sent, then R1 request is being sent, then each and every request reaches all 3 endorsement peers, E0, E1 and E2. Whenever they receive this particular request, they go through that particular request. They have gone through means they have to sign that particular request and send back the reply to the client. Assume that E0, as I require all the 3 must sign. Okay. Assume that E0 replies in 2 seconds, E1 replies in 9 seconds, But there is a problem. E2 has replied in 11 seconds, but it has not reached due to some problem to the client application. Then my endorsement, according to my endorsement policy, is I have to receive all 3 signatures. I have not received the signature of E2. Even E2 has replied, signed that particular request, but it has not reached our client application. So our client will not go forward with ordering these particular request. It would wait unless and until it receives a signed form from E2. Now E2 knows that I have signed it, but that has not reached, maybe due to this channel problem or maybe to network problem. There can be any reason for that. So when they don't receive a message, they have an upper limit for that. If I don't receive a reply back in 1 minute, then I would resend this particular transaction. So after 1 minute, when E2's reply doesn't reach the client application, again your client application sends the request to all E0 even, not only E2, all E0 even E2, because the time duration was 1 minute. Now the clock restarts now. Okay, so this is how we take care of these particular endorsement policies. In the next step, see what I have discussed. All these particular nodes, E0, E1, E2, this shows that they are processing the request or the transaction which is being sent by the client application. So E0, E1, E2 will execute the proposed transaction. None of this execution updates the ledger. Ledger is not being updated now. They are only executing. Each execution here captures the read and writes data set. What particular data sets you are reading it and what data set you are updating it. Assume I have A, B, C which are being read and E, F are being updated or you write into it. So same read and write set should be for all these endorsed nodes. You cannot have different data. So each execution will capture the set of read and written data that is called as the RW set, which now flows into that particular fabric. And the transactions are being signed and encrypted. What encryption methodology do we use? As we have discussed in previous video, public key encryption. So you use a public private key. Now each and every node, each and every endorsement node is signing through their private key and sending it back to the client application. So this is the second step. What they have received the transaction. Now they are executing the transaction, keeping a track of your RW set. R stands for read, W stands for write. So they are keeping a set of track of RW set. Why they are keeping a track? Each and every endorsed node should update the same data set. Means here if it is doing ABC and here it is doing BCD, that doesn't satisfy because they are being applying on the same transaction. So same RW set should be there for this one also, for this one also, and for this one also. If there is a change into this particular data set, RW set, definitely something is being fishy in that particular endorsement pair. So we have to look into this RW set also. After doing all these things, whatever chain codes you have to execute, execution of this transaction is being done, but we have not updated, we have not added anything in these particular ledger. So we don't update anything in our, we are only executing that proposed transaction. Okay, so what is the next step now? After the execution, you propose a response. As I told you, if this is replying in 2 seconds, this is replying in 7 seconds, and this in 11 seconds. After 11 seconds, it has received the responses for all the 3 nodes. And on these 3 particular nodes, what is the thing? Now he can send this particular transaction to the order service. So read-write sets are asynchronously returned to the application. Definitely they are not in a synchronous node. When they are replying in different duration of time, means they are asynchronously executing that particular thing. So we are keeping a track of RW sets in the asynchronous fashion only. It is being updated in 2 seconds, then 7 seconds and 11 seconds, not at the same duration of time. Okay, and the RW sets are signed by each endorser and also been recorded as a version. So whatever you have to check here on doing this, the consensus protocol which we have discussed in unit 2 comes into picture. So they have to have a consensus that all these are having the same RW set which they are updating. Then the fourth is you have to order those particular transactions. So after the transactions are being executed by the endorsers, what they are doing it? They are sending it back after first the proposal is being given by the client application to the endorser. Second, you execute those particular proposed transaction. Third is you have to give the response back. Okay, then fourth is now you are sending this information to the orderer once. So when sending the information to the orderer, now these particular executed transactions are being ordered in some specific manner which is being decided by these particular ordering services. We can have multiple Hyperledger architectures accessing these particular ordering services, or my one particular architecture can have multiple ordering services. For see, this can have a FIFO order, another may have a least execution time order, LET. So we can have n number of ordering services. Depending on what policy we require for our client application transactions, we go for that particular ordering service. So you can have this particular one specific architecture can have multiple ordering services, or multiple network can have a single ordering services. Many to many is being possible. So here the application submit the responses of the transaction which they have received to the ordering services, and the order happens the fabric in parallel with the transactions which are being connected with other applications. So you can have other applications also accessing the same ordering service. So this is the transactions are being given to the ordering services. Then you have to deliver that particular transaction. How do we deliver that transaction? These ordering services collects into a proposed block. So these particular transactions, when all of them executes, they are sending into ordering service. They look into the RW set. The same output is being generated. Same variables are being affected, and then that connects into one particular block, and this particular block is sent to each and every node, your endorsing peers and your committing peers. So the ordering services collects transaction into the proposed block. See, this is the proposed block which I have to add, which I can add into this blockchain. When can I add? After being committed by these particular nodes. Okay, so for distribution to the committing peers, the peers can deliver other peers in the hierarchy which is not shown. So what particular ordering algorithms which are being used? One is your solo, that is the single node development. You have a dictatorship in all these four particular. I am taking a scenario of this particular four. One node is acting as a main person, and other three are following the instructions given by this particular node. So this is solo. One node is having the dictatorship, and that is telling you what to do. So you don't have a consensus, you only have to follow those particular orders. And the second one is the Kafka, that is the crash fault tolerance. Obviously in a crash fault tolerance, we have minimum number of nodes, as 3. Because we should have odd number of nodes, and we have as we have seen in the Byzantine for problem, that if I have 2f plus 1 total nodes, and f nodes are faulty nodes, then I am still left with f plus 1 correct nodes. So we should have 2f plus 1, that is the odd number of nodes, and minimum nodes is 3. So it has to satisfy this particular condition for the crash fault. This is the condition which we have studied in Byzantine fault tolerance method. So now you have a proposed block, but still this particular proposed block is not being added in any of the distributed ledger. Keep this particular thing into mind. Unless and until this block is being validated, it won't be getting permanently added. Now you have delivered. First we propose the transaction, then we execute the transaction, we give the responses, we order the transaction, then we deliver it. We are giving it to each and every nodes, the endorsers and the committing nodes. Now comes the committing peers validate this particular transaction. See, this node is having a special symbol which is there in each and every one. So I told you the nodes are being committed by your committing peers. So I have only these two committing peers. This P1 is a committing peer and your P2 is a committing peer. So these committing peers validate the transaction. When they validate, each validates against the endorsement policies. How do you see that all the three nodes have executed or not, all the chain codes are being correctly updated or not, and when you have validate it with the world state, you have to validate for your current world state and validate the transactions are applied. When your transactions are being validated, then only you can add this, remove this asterisk sign and have a solid block of these particular proposed transaction. So after this, the transactions are being validated by your peers P3 and P4. When they are being validated by P3 and P4 in sync with your world state, that is the current state which is going on into the blockchain architecture. So when it is being and then if they are valid, then it is being added to that particular blockchain. If these transactions are not validated, then you have to remove this particular block, the proposed block which you have given, and have this particular transaction retain the original distributed ledger. You don't have to add this particular node. If it is validated, then these nodes are fine. I will remove this particular star and make it a solid box. But if it is not validated, then I have to remove, and all the my ledger should have only 3 blocks. The last one, after validating, we notify the transaction. When the transaction is being committed by your committing peers, then it is being notified. See, this event is being generated and it is being given to your client application also. So the your committing peers generates an event and they notify the application. The application can register to be notified when transaction success or fail. When transaction succeeds, you add, see, I have 4 blocks now. You add that particular block into your distributed ledger, and if it fails, then you have to again remove this flowered or the starred block, and you should retain these particular 3 boxes. So that is what the application will be notified by each peer when they are connected, that how the transactions the block which was coming is being added to our blockchain. So these are the 7 steps. What was the first step? First step is propose the transaction. Then after proposing, we execute the transaction. Then we have to propose for the responses that would be coming back from the client services. Now after giving the responses from the endorser to the client, then the client would give this particular transactions for the ordering transaction. When ordering is done, we have to deliver that particular transaction. On delivering it, we have to validate that particular transaction, and when the transaction is successful or failure, that has to be notified for each and every node. So these are the 7 steps, and here see we have done the validation part. See, validate transaction in the last. So the diagram which I have shown you here, we endorse first, then we order first. So endorsement policies applied here, then I have ordering services, and then we are validating the transaction. So this is the actual flow which we have for our blockchain architecture transaction flows. So what are the key benefits of this particular transaction flow? It better reflects the business processes by specifying what are the different endorsement transaction, who endorses that particular transaction, who is executing those particular transaction. Eliminate non-deterministic transaction. What are the different non-deterministic transaction? They can be eliminated as they don't get successfully executed, and so if not successfully executed, they won't be notified in the blockchain to be added as a block. Scale the number of participants in the transactions, and which results in your throughput, transaction throughput. So we can scale, we can increase the number of participants by deciding on the endorsement policies. I have 10 nodes, but if I have to decide the rights to be given to only 4, then in the endorsement policies I can decide those particular 4 nodes. So these ordering services we have discussed, they were of two types, Solo and Kafka. So I've discussed this particular three. Now the channels. The channels are those which are being privately communicating between different ledgers. So the ledgers exist in the scope of that particular channel, and the chain code is installed on the peers to access the world state. And the chain codes are instantiated on specific nodes where we have all these particular nodes have different. I have two channels here, see the red one and the blue one. So the peers can participate in multiple channels, or peer can have a single channels. So peers can participate, here I've written the multiple channels, and the execution, congruent execution of these particular tasks depends on the congruency and the performance and the scalability of that particular node to execute those particular transactions. So Hyperledger Fabric peer we have discussed. This was the peer. We have different channels. This is the peer. This peer is obviously a blue one, so it is an endorsement peer. It has two different chain codes. It has a local MSP that gives the credentials, obviously, and the different events which we have showed by this. And this is the world state, that is the states. For all different channels, I have different world states. For blue, I have blue, the red, and the green one. So for each and every channel, there would be different world states, means definitely there would be different blockchain distributed ledger. So concluding to this, we have discussed the Hyperledger V1 architecture, the first slide. Then we have discussed different types of peers, the endorsers, the committers, and the orderers. Then we have seen the transaction flow, proposing a transaction, then executing a transaction, then proposing a response, then ordering that particular transaction, deliver that particular transaction, a proposed block is being added, then you validate that particular by the committing peers, and then you notify that particular transaction. The ordering services, Solo and Kafka, we have discussed. The channels, we can have a particular endorsement peer, or the committing peer can have one or more channels or a single channel, and the Fabric peer which has local MSP for all those particular credentials. A peer can be connected with multiple channels, and for each and every channel we can have multiple world states. So coming to the end of this, these are some of the references which you can go through for this particular PPT. Thank you.